Møller Plesset perturbation theory, which is, if I remember it correctly, actually from 1934. Meaning very, very old. It's only 8 years after the Schrödinger equation. It's an application of Rayleigh-Schrödinger perturbation theory to the electron correlation problem. And the first question you always have to ask yourself when you do perturbation theory is, what is H0 and what is H prime? So you have to make a partitioning of your Hamiltonian for the system you're trying to treat into a zeroth order part and a perturbation. And the conditions for doing that is that you have to be able to solve the equations for the zeroth order part. Because that's the whole thing. The zeroth order part, you know the solutions because you need them as your basis vectors. So you have to partition your Hamiltonian in that way. Now, I mean, our Hamiltonian, that's the one from the electronic Schrödinger equation with all the electron correlation, which we know we can't solve. But is there a Hamiltonian where we actually have solved the equations? Do we have an Hamiltonian which eigenfunctions we actually know and which eigenvalues we know? We could take the Fock operator. So if you take H0 to be the sum over, let's see which index here, the sum over all Fock operators, so that's the sum over from 1 to the number of electrons of those Fock operators, and I think I wrote them last week also with capital letters, with capital F, which is sort of a bit against my taste because it's a one electron operator, so it should be a small f, but anyway, to stick with the notation in the book, it's a capital F, I think. So it's a sum over all those Fock operators. So it has, what Nikolai said, it has the kinetic energy operator for each electron, it has the electron nuclear attraction operator for each electron, but it also has the effective averaged electron-electron repulsion operator. So let's write that out a bit more in detail. So I have I from 1 to the number of electrons, and I have a big parenthesis. So I have this HI, which is kinetic energy plus electron nuclear attraction operator. And then I have to have this Hartree-Fock potential, the averaged electron-electron repulsion. And hopefully from your Hartree-Fock week, you remember that this is then obviously a sum over all the other electrons, J. And then there are two operators. There's the so-called Coulomb, and because we have an antisymmetrized wave function, we're using Slater determinants, we also get this exchange operator, K. So that's a Hartree-Fock. That's the Fock operator. And now we sum over, which we normally just use for one electron. The Hartree-Fock equations, like the Kohn-Sham equations, are one electron equations. So we let this act on an orbital and get some orbital energy times the orbital. That's the Hartree-Fock equations. But now we sum over all electrons and we get what one could call the Hartree-Fock Hamiltonian. And we use that as a zeroth order. Before I continue, do you all remember how those look like? Some nick, but anyway, let's write them up for a second. The Coulomb operator, that I actually can really write up what it is. That's an integral, obviously over the distance between the two electrons, and this is electron I, because I mean it's operator in the equation for electron I. So I have Ri minus Rj, the distance between the two. And then I have up there, I have the electron density of electron J. And the electron density I get as the norm square of the orbital describing the other electron. So that's a spin orbital J, and it has to be spin orbitals. So that's not the position vector, but it's the position vector plus the spin of the second electron. I have to, and the volume element also includes, or it has to include spin integration. So that's a Coulomb operator. It's essentially the interaction with the charge density. The exchange operator, unfortunately, we can't write up like this. We only can write it up acting on something. So I could write it like, let it act on, what should I act? On psi I then. And then I can write it up as, again, an integral. Same Ri minus Rj. And then psi j complex conjugate of electron j. And now comes why I have to write that with a function here, because now I get psi I of electron j. And I integrate over space and spin of electron j. And then again here psi j of electron I. Where you can see here you have that exchange, why it's called the exchange operator. So I exchange the, well, I don't exchange, well, I exchange those, yeah. The spatial orbitals, or the electrons, but never mind. So those are those two. Now that's our zeroth order Hamiltonian. What are then our zeroth order wave functions? If that's our zeroth order Hamiltonian, what are those I or J's that we used before? Which are the eigenfunction to that Hamiltonian, but what are they? These are all Slater determinants, determinants made from the Hartree-Fock orbitals. So we have our Hartree-Fock orbitals, but these are many electron wave functions, so it's all the Slater determinants, which means it's the Hartree-Fock Slater determinant, it's all single excited determinants, all double excited determinants, all triple, up to all n electron tuple excited determinants. Which means it's precisely the same determinants which we had last week. It's precisely the same determinants which we're using in configuration interaction. And the full set of states here is the same full set as we have in full CI. So it's not the basis functions, it's not our expansions which are different. The only difference is how we get the coefficients. In CI last week we used variational principle. Here we use perturbation theory in order to get the coefficients. They're going to look different, but many electron basis functions are precisely the same. So here we know, and those we know. But it also means this set, although it's still finite, as long as we have a finite one electron basis set. As long as we have a finite number of orbitals, this set of determinants might be large, but it's finite, which means it's not complete. So again, like last week when we did CI or MCSTF, we're going to solve those equations only within the space given by our basis set. So we're going to solve them sort of exactly in that space. But not really exactly, because that's basis limit. Good, so that's H0, that's the, and then, oh yeah, what are the zeroth energies then? What are the EJs? The Hamiltonian is the sum of the Fock operators. The eigenfunctions are Slater determinants, which actually means that all Slater determinants are eigenfunctions of the sum of Fock operators. What are the eigenvalues for that? This is the sum over.
Orbital energies.
That's the sum over orbital energies. Okay, and all the ones which you have used in that determinant, which are sort of occupied in that determinant. So if it's a single excited determinant, it's all the ones which you have in that. So let's remove that occupied, not to mislead you that you believe it's only Hartree-Fock occupied orbitals. Why is that? Because you have this one acting, that's a sum over one electron operators, acting on a product of one electron functions. Which means each operator is going to act on its function, and the eigenvalue of the Fock operator with a spin or spatial orbital is an orbital energy. So you end up having the sum over the orbital energy of the energies of all those orbitals which you have included in your Slater determinant. So that's our zeroth order energies, are just sum of the orbital energies.